Welcome everyone. We are going to be looking at the gravitational force, and it's so exciting because you've heard bits and pieces, and now we're going to put it all together, and it's going to be lots of fun. So, have you ever thought about why will an object, when it's thrown in the air, come back to Earth? You all know it happens, and you've all heard the saying, what goes up must come down. But why? Why does it come down as fast as it does? Why does it stop when it gets to the top and then comes down? Why are we stuck on Earth? Why can't we just jump into space? Well, we wouldn't be able to breathe in space, but that's besides the point. Okay, so that's what we're looking at. We're looking at gravitation, so we're going to look at Newton's law of universal gravitation. We're going to look at the equation, which is a little hairy, but we're good. We're going to look at the difference between little g and big G. We're going to look at the graphs associated with this. And then we're going to look at different types of questions, because there's lots of ways we can ask this. Our key words are Newton's law of universal gravitation. On that note, we know that there's 3 Newton's laws. First law, second law, and third law, okay? This is like a 4th law, but it has a special name because it's to do with gravitation. All right, so you need to be careful. We also use the word universal in the title because at our current understanding of the universe, this law works anywhere. Whether you're on Mars, whether you're on the moon, Earth, whatever, according to what our current understanding is. Maybe that'll change, who knows? That's why it's universal. We're then going to talk about the concept of gravity and the universal gravitational constant. We don't like constants, but it's okay. Let's start with Newton's law. You all know the story, I'm sure. Somebody's told you we have no, it was Sir, he was a knight, Sir Isaac Newton sitting under a tree, and then the apple fell on his head, and he went, ooh, gravitation. Not really the way it happened, okay? He was sitting under an apple tree, and then he watched how the apples fall to the ground. And being the incredible scientist he was like, why did that happen? And then he started doing investigations. He then came up with the law, which is a little long-winded, but it's fine. And he said that each particle in the universe attracts every other particle. You have to say attracts with a gravitational force. We're saying gravitational force because we also get electrostatic forces. That is directly proportional, whoopsie, there it is, to the product of their masses, product very important there, and inversely proportional to the square of the distance between their centers. Often with this one, we forget about the fact that it's the product of their masses and it's the square between their centers. That last part between their centers is really, really important. For big objects, where their center is, makes a big difference into the force of attraction that will be felt. Okay? Now, we're going to look at the equation. The equation looks far more complicated than it is. The nice thing, it's on your information sheet. So it's F, force, G, M1, M2, and R squared. Let's go through what each of those mean. So F is force. That's nice. Measured in newtons. That's easy enough. G is a constant. And G is 6,67 times 10 to the minus 11. It's tiny, but it has to be there. And we will investigate it where we get the G from, okay? I'm going to come back to the units. Mass is, M1 and M2 are masses. We call them M1 and M2 because it's two bodies, it's two particles. So we have to differentiate between the two. Of course, it's mass, so that has to be in kilograms. And R is the distance between their centers. That must be measured in meters. Here we need to be careful because we're going to get situations where I'm going to give you distances in kilometers. You must then change it to meters. We'll get to that. When we look at the units for G, the units need to give me newtons. So this is newtons, okay, per kilogram to the -2 per meter squared. Is that where yeah, then it'll cancel itself out. We're not worried about the units, okay, because it's going to sort itself out along the way. We're going to use that constant often, the fact that G is constant. So keep that in the back of your minds. Then we need to look at the difference between little g and big G. And of course, when we go G and G, little g, big G. Okay, very important. So little g is acceleration due to gravity. Little g is an acceleration. It's not a force. Okay, and little g, that acceleration due to gravity, is a consequence of the planet we're on. So it changes. It's completely dependent on the planet. We now need to look at the difference between little g and big G. They're both G, but they mean different things, okay? And it's not just them being different because one's lowercase and one's uppercase. They're different concepts. Let's look at those. When we look at acceleration G to gravity, here, this is an acceleration. It changes depending on the planet, which is what I've got here. And remember, on Earth, acceleration due to gravity is 9,8 meters per second squared. If you go to the moon, which is 1/6 the size of the Earth, the gravitational force there, the gravitational acceleration you feel, is 6 times smaller than on Earth, which is why people can bounce on the moon, because there's less gravity. G is a universal constant. It does not change. It's the same value no matter where we go in the universe. Same value. We're done with some theory, so we're going to take a short break, and I'll see you in a couple of minutes.